Okay, so the next question that we have is exercise number 10. Exercise number 10. I would characterize this exercise both as a bad exercise and both as a very good exercise. Bad in the sense that you would have to think a lot to basically find the answer, but good in the sense that you basically need to have a very good understanding of the concept so that you can actually answer the question. Sometimes thinking in terms of such problems give you a very good understanding of the concept. So now the question is, give an example of a relation. Give an example of a relation which is symmetric, but neither reflexive nor transitive. So a relation that is symmetric means that basically if A comma B belonging to R, that has to imply that B comma A also belongs to R. That means that the relation is symmetric. Now, if it's not supposed to be reflexive, then A comma A is not supposed to belong to R, meaning that the condition for reflexive, is that A comma A belongs to R for all A belonging to the set A. So this should not be the case. If you want the relation not to be reflexive, this should not be the case. And you don't want it to be transitive. The condition for transitive is, as you know, is that basically if, let's say, some x comma y and some y comma z belongs to R, that has to imply that x comma z also belongs to R. So if you don't want the relation to be transitive, then this shouldn't be the case either. But this should be the case. Now you need to think of some situation in which case basically this happens, which means that basically the first one is the case, but these two are not simply the case. So now I could actually solve this problem based on the solution, but I don't want to do that. So let me come up with an example of my own, and then I'll explain the example to you. Okay, so basically what I assumed here was that basically I assumed that these relations are supposed to be defined in terms of algebra, meaning that, for example, you're supposed to, for example, write some set A is equal to, for example, so basically such and such a set, and then R is equal to, for example, all the ordered pairs, for example, A comma B, such that, for example, B is equal to, for example, there is some algebraic relationship between A and B, and so on and so forth. But it's actually not that way, because this makes things a little bit complicated. Because you have to, it's just like juggling balls in the air. You have to make sure that basically the relationship, the algebraic relationship between A and B is such that basically, for example, is such that the relation is symmetric but neither reflexive nor transitive, and then if you change one thing, then the other one changes as well, and so it's a little bit tricky. But what we want to do here is that we want to make sure that basically that we understand these at least in terms of sets, right? Which means that, for example, in the case of the first example, I can say that, for example, let A be equal to, for example, the set, for example, 5, 6, and 7. And define a relation on A. Define a relation on A as, for example, R is equal to 5, 6 and for example 6, 5. So since you have 5, 6 and also 6, 5, so then of course the relation is reflexive. It is reflexive. I'm sorry, it is symmetric, right? And so basically you can say that the relation R, you can say that the relation R is not reflexive, as basically 5, 5, 5, 5, 6, 6, and 7, 7 do not belong to R. Belong to R. And we are saying this based on the fact that the condition for R to be reflexive, is that A comma A has to belong to R for all A belonging to A. So since that is not the case, meaning that since 5, 5, 6, 6 and 7, 7 do not belong to R here, then you can say that the relation R is not reflexive. And of course, it's not transitive and you can say that basically you can of course argue that 5, 6 for example belongs to R and 6, 5 belongs to R. So 5, 6 does belong to R and 6, 5 does belong to R, right? So and therefore R is symmetric. R is symmetric, meaning that the condition for R to be symmetric is basically if x, y belonging to R implies that y, x also belongs to R. That is the condition. Now over here you can see that 5 comma 6, you can see that 5 comma 6 belongs to R, and 6 comma 6 belongs to R. 5 comma 6, 6 comma 5. 6 comma 5 belongs to R, but 5 comma 5 does not belong to R. Therefore, R is not transitive. R is not transitive, right? So that's basically one example where R is basically, whatever the question over here, what R is symmetric but neither reflexive nor transitive. Another question, the second part of this question is that you want to give an example of a relation. Give an example of a relation which is number 2. This is the second part of this question. Transitive, which is transitive but neither reflexive nor symmetric. Right? Neither reflexive nor symmetric. Okay, so it's supposed to be transitive, right? So what you can do now, you can consider the relation R. Consider the relation R in R, meaning the set of real numbers, and this is your relation defined as basically R is equal to basically all the ordered pairs A comma Y, such that A is less than B. A is less than B, right? Now for any A belonging to R, we have A comma A does not belong to R. For any A belonging to the set of real numbers, we have A comma A does not belong to R. And please pay attention to the fact that when I write this is basically the set of real numbers, this denotes the relation that we have here, right? So again, over here, for example, this is the set of real numbers, this is the relation that we have. So what that means is that, of course, in this case, as you can already see, basically for every A belonging to the set of real numbers, since A is less than B, so of course A is not equal to B. That means that there is no way that you can get A comma A as any of the elements of R. So A comma A does not belong to R. And so you can say that, and the reason there is a good reason over here, meaning that since A cannot be strictly less than A itself, A cannot be less than itself. Less than itself, right? So that's basically that. And therefore you can say that basically R is not reflexive. R is not reflexive. Now to basically for the part that it is symmetric or it is not symmetric, are not symmetric, in order to show that basically you know that for example 1, 2 belongs to R. 1, 2 does belong to R, but 2, 1 does not belong to R, as 2 is not less than 1. Is not less than 1. And therefore R is not symmetric. R is not symmetric. Now for the case that R is transitive, so the way that you can show it is that, for example, suppose that for example, suppose that x comma y and y comma z belong to R. So this implies that x is less than y and y is less than z, which implies that x is less than z. X is less than z. So which means that x comma z belongs to R. Which means that basically R is transitive. R is transitive. So that's another example, for example. Now the next part of this question is that you want to give an example of a relation relation which is reflexive and symmetric, but not transitive. Okay. Now for this part, you can argue that basically let A be equal to, for example, let's think of some set as, let A be equal to, for example, 4, 6 and 8. 4, 6 and 8, and define a relation R. On A as, for example, R is equal to this set of elements 4 comma 4, 6 comma 6, 8 comma 8, that makes it reflexive, 4 comma 6, 6 comma 4, 4 comma 6, 6 comma 4, and 6 comma 8, 8 comma 6, 6 comma 8, 8 comma 6. That makes it symmetric, and so that is it is reflexive, symmetric, but of course it's not transitive. 6 4 comma 4 is, well, it's not supposed to be, which is reflexive and symmetric but not transitive. Well, it seems to me that this is actually transitive, because 4 comma 6, 6 comma 4, 4 comma 4 is there, and 6 comma 8, 8 comma 6, 6 comma 6 is also there. But of course, well, you could argue that, for example, 8 comma 8, 4, so 8 comma 6, well, it's of course not transitive, right? So then you can say that R, basically the relation R is reflexive, since for every A belonging to A, you can say that for every A belonging to A comma A belongs to R, meaning that you have for every A belonging to A, meaning for each and every of these elements, 4, 6, and 8, you have 4 comma 4, you have 6 comma 6, and 8 comma 8. So basically R is reflexive. For the fact that basically R is symmetric, you can say that basically for every, for example, A and B belonging to, let me see. So the condition that we have for symmetric, we said that basically the condition that we have for symmetric, we said that basically if A1 comma A2 belongs to R, so for symmetric, we said that if A1 comma A2 belonging to R implies that A2 comma A1 belongs to R for all A1 A2 belonging to A, for all basically for all A1 comma A2 belonging to A. Now let me rewrite this part, and then there is something important that we need to talk about here. Okay. So basically the condition that we use for R to be symmetric, we say that A1 comma A2 belonging to R implies that A2 comma A1 belongs to R, right? For all A1 comma A1 and A2 belonging to A, right? Now, I suppose you have taken the course related to mathematical reasoning, and you know that basically this statement can be written as A1 comma A2 belonging to R implies that basically A2 comma A1 belongs to R for all or basically you can read this as for every or for all A1, A2 belonging to A. Now you might be thinking that you could write this statement as, for example, as this way. What I'm going to do is that I'm going to take this part of this statement and just take it to the beginning of the statement, meaning that I'm going to say that for all A1, A2 belonging to A, right? And then A1, A2 belonging to R implies that basically A2, A1 belongs to R. Now these two statements are completely different statements, meaning that when you say for every A1, A2 belonging to R, when you say for every A1, A2 belonging to R, A1, A2 belonging to R implies that A2, A1 belongs to R. What that means is that for each and every element in A, meaning that if you have some set A over here and you have all of these elements in A, for each and every of these elements, if A1, A2 belongs to R and you have some set A over here and it's basically all of these ordered pairs, right? So for each and every one of these elements, then if basically A1, A2 belongs to R, if that is the case, then A2, A1, then it has to imply this one, meaning that if A1, A2 belongs to R, then A2, A1 has to belong to R as well, right? So that's what this statement is saying. Now this statement is saying that A1, A2 belonging to R, that has to imply this one, meaning that if this is the case, this has to be the case for every A1, A2 belongs to R. Now in the case of these two statements, I would say with a lot of caution that there is actually, well, I would say most probably, there is actually no logical difference between these two statements. But in many cases, and probably even including this particular case, when you change the order of basically, when you change the order of these quantifiers, this is called a quantifier, right? This thing over here is called a quantifier. So when you change the order of these quantifiers, the whole meaning of the whole statement is going to change. So yeah, you need to be careful when you basically, whenever you want to write a statement, you need to be careful where in your statement you actually place that quantifier. And when you want to read a statement, you need to be careful how to make sense of the statement that you read, depending on where you find the quantifier in the statement, right? So that's basically that. So now let's get back to the example that we had here. So the example that we had was basically we had A was 4, 6, and 8, and we wanted we defined the relation R on A as this. And so we wanted to show that this relation is symmetric, right? So we are saying that basically A1, A2 implies that belonging to R implies that A2, A1 belongs to R for all A1, A2 belonging to R. And as you can see over here, of course, 4, 4, if you were to basically check the symmetry, 4, 4 is symmetric with itself. So you have no problem there. 6, 6 is symmetric with 6, 6, so you have no problem there. 8, 8 is symmetric with 8, 8, so you have no problem there. 4, 6 is symmetric with 6, 4, so you have no problem there. And 6, 8 is symmetric with 8, 6 based on this rule, and so you have absolutely no problem whatsoever. And so what that means is that then you can say that basically A1, A2 belonging to R implies A2, A1 belonging to R for all A1 and A2 belonging to A, which is the case, and therefore R is symmetric. And therefore R is symmetric. Now about R being transitive, about R basically actually not being transitive, but not transitive, R not being transitive. So how can we show that R is not transitive? The condition that we use for R being transitive, not being transitive, but for being transitive, is that if basically A1, A2 belonging to R and A2, A3 belonging to R implies that A1, A3 belongs to R for all A1, A2 and A3 belonging to A, right? So what that means is that now here you can argue that, for example, you have 4, 4, and you have 4, 6, and then 4, 6 is also there. Or you can argue that you have, for example, 6, 8, 8, 6, you have 6, 6 is also there. And you can argue that so how do we show that R is not transitive? 4, 6, 6, 8. 4, 6 and 6, 8. And 4, 8 is not there. As you can see, 4, 6 is there. 6, 8 is there. So basically you know that basically now 4, 6 belongs to R, and also 6, 8 belongs to R, but 4, 8 does not belong to R, and therefore R is not transitive. R is not transitive, right? So that was another example here. that was another example here. Let's do the part 3 we already did. So now part 4 of this question. Part 4 of this question, we need to 29. You want to give an example of a relation which is reflexive and transitive, but not symmetric. So part 4, basically you could argue that you could define a relation R in R. You could define a relation R in the set of real numbers as R is equal to, for example, A comma B, such that A cube is greater than or equal to B cube. A cube is greater than or equal to B cube. Now we want to show that this is reflexive and transitive but not symmetric, right? So to show that this is reflexive, basically what you need to do is, if A comma A belongs to R, for every A belonging to A, right? So of course, as you can see here, we have A cube is greater than or equal to B cube, right? So you can say that clearly, A comma A belongs to R as A cube is equal to B cube. So we have no problem there, and so basically we can say that basically R is reflexive. So remember that whenever you want to define a relation which is reflexive and also other things apart from being reflexive, well, of course, if I write, for example, this relation as R is equal to basically ordered pairs A comma B, such that A cube, for example, is greater than B cube, then of course this is not going to be reflexive because basically A cube is not equal to B cube. Over here, A cube is not equal to B cube. And so what that means is that basically then A comma A cannot exist in R. So when you put this equal sign over here, then you can make sure that the relation is reflexive as well. Now about being transitive, you can say that basically let some x comma y belong to belong to R, and y comma z also belong to R. Now these two imply that basically these two imply that basically x cube is greater than or equal to y cube, and also basically y cube is greater than or equal to z cube, which implies that basically x cube is greater than or equal to z cube, which implies that x comma z belongs to R, right? So if x comma y belongs to R, y comma z belongs to R, and if x comma z belongs to R as well, then that means that basically R is transitive. R is transitive. Let me see how they have solved this problem. Yes. Now about the part that it is not symmetric, let's suppose that some a comma b, for example, not symmetric. Let's suppose that, assume that a comma b belongs to R, which means that a cube is greater than or equal to b cube, right? Based on what we have here. So if a cube is greater than or equal to b cube, basically so to show that R is symmetric, if a comma b belongs to R, which implies that basically a cube is greater than or equal to b cube, you have to show that basically b cube is also greater than or equal to a cube, so that then basically b comma a belongs to R as well, and then that means that basically a comma b belongs to R, b comma a belongs to R as well, and so that means that then R is just simply symmetric. But this cannot exist. But since a cube is greater than or equal to b cube, then of course you cannot say that. That means that you cannot say that b cube is greater than or equal to a cube as well. That just doesn't, it's just not possible to say that, which implies that basically b comma a does not belong to R, which means that basically R is not symmetric. Okay. Now the way that they have solved this problem, I mean, this was basically using logic, but another way that you can solve it, you can say that, for example, 2 comma 1 belongs to R, as basically 2 cube is greater than or equal to 1 cube. So this is equal to 8 is greater than or equal to 1. But 1 comma 2 does not belong to R, as 1 cube is less than 2 cube, right? That's the exact same thing that we talked about before. And so then you can say that R is not symmetric. Right? So that was basically the fourth part of this question. And the fifth part of this question is that you want to give an example of a relation which is symmetric and transitive. Symmetric and transitive, but not reflexive. Let's see how we can do that. Okay, so the next part of this question, you can answer it in this. Basically, you can say that, for example, let's consider some set here. Let A be equal to, for example, some set like, for example, -5 and -6, right? And define a relation on A as, for example, R is equal to -5, -6, -5, -6, -5, -6, and -6, -5, and -5, -5. Now, in order to show that basically this relation is symmetric, you want to show that basically -5, -6. So basically you can see that -5, -6 is symmetric with -6, -5. So you have no problem there. And also -5, -5 is symmetric with itself. So you have no problem there. So you can say that for basically, you can say that A comma B belonging to R implies that B comma A belongs to R for every A and B belonging to the set A, for example. Which means that basically R is symmetric. R is symmetric. In order to show that basically R is transitive, so basically you have -5, -6, and so you can see that -5, -6 belongs to R. -6, -5 belongs to R, and then -5, -5 also belongs to R. Over here you can see that -6, -5 belongs to R, -5, -5 belongs to R, and so -6, -5 also belongs to R. So you have no problem there. And of course it's important to note that each and every possible element that you can take together must be taken together, and then you can decide whether the relation is transitive or not. Meaning that, for example, these two, you can take them together because the second element here is -5, the first element here is -5, so you can't take them together. Meaning that we say that basically we say that if A comma B belongs to R and B comma C belongs to R, both of them belonging to R, has to imply that A comma C also belongs to R for every A, B, and C belonging to A. That is the condition. That means that wherever you find two elements in the case of which basically these two B's are present, then you have to take them together, and that has to imply that A comma C also belongs to R. So you can see that, for example, over here -6 comma -5 has to belong to R as well, and which is this element over here. Now over here these two elements can be again taken together, and so -5 comma -5 has to belong to R, which is this element here. But these two elements, you cannot take them together, because over here you have a -6, over here you have, over here you have a -6, over here you have a -5, and so they just don't go together that way, which means that since you cannot make this assumption, then this implication doesn't have to be the case either, and so you have no problem there, right? So since this is the case, in the case of this relation R, you can say that R is transitive. R is transitive. Now, to show that basically, to show that R is not reflexive, so basically the condition for being reflexive is that A comma A, why did I put this thing over here? So not reflexive. The condition is that A comma A has to belong to R for every A belonging to A, right? Now over here you can see that basically -5 and -6 belongs to A, and -5 comma -5 belongs to R, and -6 comma and -6 comma -6 does not belong to R, right? So since -6 comma -6 does not belong to R, therefore R is not reflexive. Right, so that is basically that. Okay, now this was question number 10. The next question that we have is question number 11 that we will talk about in the next video. I'll see you in the next video.